What did you type in to find that, Sean?
I just typed in Haiti and Dominican Republic border picture.
Oh, yeah, there you go. Yeah, there's another close-up. Yeah. Okay, so let's start looking into the chemistry a little bit. So 4.3 is just called biomass as a solar energy store. We mentioned photosynthesis. I showed you photosystem 1, or a cartoon of it. The molecule itself is smaller than light, so you can't actually see the dang thing. But 4.3, biomass as solar energy store. Just while I'm thinking about it, I want to give you a quick preview to this other paper that we're going to read. Have we posted summary 2 yet? This might actually be a really good summary 2 for this class. Let me find it really quick while I'm thinking about it. Give you a little preview. Paper notes. Shramsky, College of Engineering, University of Georgia, and the Department of Biology, University of New Mexico, Albuquerque. Human domination of the bio. So I think this would be a great summary too for this course. This is actually just published in Proceedings of the National Academy of Sciences. There aren't too many higher regarded journals than this one. And the reason it just came to mind, because I'm looking at just the title of this section, Biomass as a Solar Energy Store. These guys call it a chemical battery. You know, the authors of our textbook call Solar Energy Store. These authors go so far as just to call biomass a chemical battery. So where's that coming from? Let's go back into the chapter. And what we're looking at are 6 CO2s. And I think now that figure that I was a little surprised by is going to make a little more sense. Okay, so here comes the CO2 coming in from the air. A plus 6 H2Os, so there's your water, plus a little light, becomes, and now there are a lot of other steps along the way. When I kind of went down that little photosystem 1 rabbit hole, you can see there's all kinds of enzymes that make this happen. But these are just your inputs and your outputs of a tremendously complex set of molecular machines. So this becomes glucose, C6H12O6 plus 6 oxygens. And just for fun, let's make sure that the chemistry is correct. So on the left side, we've got 6 times 2, that's 12 oxygens. And then another 6 for a total of 18 oxygens on the left side. Now let's look at the right side. We've got 6 oxygens right here. So for oxygen, we've got 6 plus Again, 6 times 2 is 12, equals 18. That checks out. So conservation of mass is still at work here. Now we've got carbons. Right here there are 6 total, and all 6 of those carbons from your 6 individual CO2 molecules. We talked a little bit about the structure of the CO2 molecule, went to the periodic table, so I think you're kind of familiar with what that is now. On the right-hand side, all 6 of those carbon atoms, I think I might have said molecules, all 6 of those carbon atoms from your CO2 molecule are now part of your glucose molecule. And now if we look at the hydrogens in the water, there are 12 hydrogens right there. All 12 of those hydrogens from the water are consumed in a single glucose molecule, H12, so everything checks out. Okay. As mentioned in the book, says the first product on the right, the equation is glucose, C6H12O6, a carbohydrate, obviously, and that's just straight up what your brain burns. That is the fuel for your brain. Plants also use that as a fuel, but glucose is also the building block for virtually every other carbohydrate. It's a monosaccharide, lactose, maltose, and I think there's one other, dextrose, 2 or 3 different disaccharides, and then kind of on up the chain. Starch being a longer one, and then as you move further up, you get into cellulose, hemicellulose, different sugars hanging off of them. The celluloses and hemicelluloses are more or less the skeletal system of a plant. So it's everything that's allowing that big green and brown thing to stand up. From there, we get into lignin, and since I showed you photosystem 1, I also want to show you lignin. This might be one of the, this is actually not quite as complex as photosystem 1, but that's the best we can do with the lignin molecule. It's beautiful. It's huge. It can be a pain in the tuchus, though, for some biofuel applications because it's so hard and tough. It's tough to break that thing back down into an easily combustible, pyrolyzable, what have you, molecule for making gas. Lipids are also mentioned, and so are proteins. So basically with that, sugars, fats, and proteins are the 3 primary biological building blocks of every other biological system. Enzymes are also mentioned. It says specialized proteins that act as catalysts that enable the reactions to occur at ambient temperatures and pressures. That very last sentence, at ambient pressures and temperatures, is really key if we're going to actually do what's so-called biomimicry at the nanoscale. So biology has figured this out over the past several billion years, and that's where I think we could make a lot of good progress and get away from some of our high temperature, high pressure technologies that we currently use. Talked a lot about hydrocarbons. Looking at this lignin molecule, let's see if I can maybe blow it up a little bit more. Yeah. Everything down there, it's just hydrogen, carbon, and oxygen. Every one of those rings is 6 carbons. In a little ring, they don't bother to write out the full, write out all the C's. But pretty amazing. We need to figure out how to do that and make better plastics, right? Because it's the same thing. We've been studying plastics lately. It's just carbon and hydrogen in a specific configuration. But Lignan's something else. Okay. All right, so as promised, I do want to look at this conversion efficiency box. That's box 4.3. Box 4.3. So we're going to look at 1 hectare. And here's where, and this is what I would really like to be able to do at my own house. I would love to be able to get to the point where all of my energy just came from the sun. There's this whole concept that Jared Diamond came up with called the photosynthetic ceiling, and it's basically the idea is that you're deriving all of your primary energy just from the sun and not tapping back into the fossil fuels that we studied there in 101. So pumping, heating, maybe making light. It'd also be great, and this is something that Ted Carnes has been able to do in Pennsylvania. He's now to the point, and I need to check in with him to verify this, but he was trying to get to the point where he was generating enough methane and ethanol from his own biological processes to use the methane and the ethanol for transportation and heating. And so you can imagine just making both of those compounds for doing exactly that, moving around and for staying warm. But 1 hectare is 10,000 meters squared. Meters squared. And so they're looking at a solar incidence of 1,000 kilowatt hours per square meter per year. What's that mean? 1,000,000 kilowatt hours? No, 1,000,000 watt hours. So let's just think about this. How many kilowatt hours is that per square meter per day? Let's just run that really quick. So because you see a number like that, I always will instantly say, does that get back to our solar constant that we were talking about before, our phi? So let's do that really quick. So 1,000 divided by 365 equals, it's only 2.7. Seems a little low, but depending on where you are in English, Missoula is at 4.4, if I'm not mistaken. These guys are only 2.7, so not a whole heck of a lot to work with, but I'll believe it. 2.7 kilowatt hours per square meter per day. Okay, so we're going to start there. So this equals 36,000 gigajoules. Okay, so after losses, about 1/8 of it reaches the crop at the right time. So let's look at this. 12% hits, so the leaf, so I'm just going to, in fact, I'll use this symbol now. So eta leaf, so that eta is the symbol for efficiency. If you remember from 101, that's just energy out over energy in. So equals 0.12. So if we take 36,000 times 0.12 equals, there's your 4320. So that gives us 4320. And so you could imagine if you were a tree and trying to be as successful as possible, you would put energy into making leaves so that you could harvest it in the other tree or blade of grass or whatever it gives you. But it has to be a growing leaf, something that's actually alive and putting energy into metabolism. Okay, 50% is photosynthetically active. So eta photo equals 0.5. What does that mean? Well, it's very similar to some of the spectra we were looking at with the PV systems. So this is figure 4.3. And I'll just let me just read here from the book. It says the remaining losses shown in box 4.3 are specific to the interaction between the plant and sunlight. A leaf responds only to a part of the solar spectrum. The pattern of absorption is shown in figure 4.3. Note the dip in the green region. A leaf looks green because it absorbs less green light than red or blue. So the figure's a little bit misleading, but what the leaf is actually taking in are the two things on the hump, the blue and the red. Our eyes tend to be tuned so that we can actually see green things better than other things, just because that's what's typically around us. Okay, so that's the absorption efficiency. So that takes us down to 2160. So now I'm going to do eta capture by growing leaves. That's 0.85. So even though it's photosynthetically active, the capture rate is not 100% efficient, even though it's in the right bandwidth. It's not 100% efficient. So we're looking at 1860 gigajoules. 1836. Oh, thanks. Yeah, 1836. And then 21 goes into storage. So eta store. The rest is just going into metabolism, 0.21. So now we're all the way down to 386 gigajoules. 40% of that is lost in respiration to sustain the plant, or lost in photorespiration leaving. Respire. 0.40. That leaves us with only 231 gigajoules. Gigajoules. So the upshot is that is only 0.64 percent efficient, or eta equals 0.0064. Kind of weird. That's the reality. Yeah. Okay. There are a couple questions on this next little topic. It says plants of the temperate region are referred to as C3 plants, because the first product of photosynthesis actually contained 3 carbon atoms rather than the 6. So kind of scroll back up here. this is, like I said, this is kind of the big picture of photosynthesis where you're left with the sugar, but there are several intermediate steps along the way. And so it just mentioned C3, there are only 3 carbon atoms rather than the 6. It says the fundamental biochemistry of the C3 photosynthesis means that 21% of the energy of absorbed light is converted into energy content of fixed carbohydrate. Finally, 40% of this fixed energy is used in respiration, as we just saw. It says in C3, too much light relative to the CO2 available can lead to damage through the main photosynthetic enzyme producing a toxic molecule called phosphoglycolate, or rather than the C3. This is a pretty weird and confusing set of paragraphs, so I'm just going to keep reading here and wrap our heads around it. It says plants from tropical areas are at greater risk from light-induced damage because of the higher light levels. Some tropical plants, especially those in the grass family, maize, sugarcane, miscanthus, effectively concentrate CO2 in the cells where photosynthesis is carried out, so there's never a shortage and no risk of damage. So they're actually sort of breathing this in and holding their breath a little bit. They produce a 4-carbon molecule as the first product of photosynthesis, while the fundamental efficiency in these C4 plants says the photosynthetic efficiency is less than the C3, but they can potentially produce higher yields of biomass because they don't have the wasteful photorespiration or losing water over the course of photosynthesis. So these guys have, so you could sort of tell how if you're going to do some bioengineering, you would want to pay a lot of close attention and what the light levels are and put a strategy together for growing plants. And finally, it says for C4 plants grown in tropical areas, the 5.3% of box 4.3 might increase to perhaps 6.7, giving an overall efficiency closer to 1%. Furthermore, good crop rotation management can increase the fraction that's captured and used. It says, nevertheless, plants, this is kind of surprising, because nature's been doing this for a while, plants remain less efficient solar energy converters than PV, which can be 10 to 20. But they're cheaper per square meter. So there's always a trade-off. All right, well, I'll call it good there for today. I'll let, I'll pick it up in 4.4 on Thursday, and then I'll let Tim and Mark take it from there.
Oh, so you haven't worked. I haven't seen him for a while.
Yeah, he's around.
What's he doing now, Lee?
Well, he's still, he's been working over at Albertsons for a while now. They've got,
Albertsons are still.
what's that?
Some of the Albertsons sell.
Okay, see you, Sean.
Yeah.